All right. So we've been talking about force of gravity for quite a while, right? Practically since the beginning of the semester. We also said that force of gravity is a non-contact force, right? As in long range. But we never really talked about where force of gravity comes from and exactly how the objects interact at a distance. So Newton's law of gravity, that's what tells us how objects interact. So let's draw this picture. We'll have two masses whose centers are separated by distance r. So the two masses are not in direct physical contact. Their centers are separated by distance r. So Newton's law of gravity, which is also called universal gravitational law, tells us that we can calculate gravitational force between these two objects by writing F with a subscript capital G. So F sub little g, we already dealt with. This is F sub capital G. It's equal to big G, m1, m2 over r squared. So force of gravity between two masses whose centers are separated by distance r can be calculated using this equation. G is called universal gravitational constant. And it's equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. So it's one of the fundamental constants of nature. Notice how it has really weird units? Well, this really weird units is so that everything else works out. So big G is Newton meter squared over kilogram squared. Then you have two masses, which are both measured in kilograms. And then you're dividing by r squared, which is meter squared, right? So kilograms and meters cancel out, and then we end up with newtons for units of force. So there are several constants like this. We're not really going to encounter them in this class anymore, but there are several what we call fundamental constants that have really weird units. And again, the purpose of those weird units is to have all the other units in the equation work out. Okay? Now notice how this law, this equation, has r squared in the denominator. So we would write it like this. F sub g is proportional to 1 over r squared. That little squiggly thing, that's proportionality. Okay? So it means force of gravity goes as 1 over r squared. So any law that has that form, that has the 1 over r squared in it, is called inverse square law. Okay? So inverse means that r squared is in the denominator. Inverse square law. So there are several forces and some other quantities that follow inverse square laws. They're actually quite important because there are several characteristics of that law that are true for all of those forces and all of those other quantities. Okay, so I want to look at a couple of them. First of all, if I graphed force of gravity as a function of r, 1 over r squared kind of has this shape. Okay, so there are two important parts of this graph, two important pieces. So one is this piece and one is this piece. So if you think back to math where you analyze different kinds of functions, you probably remember talking about asymptotes. So both axes in this case are asymptotes to this graph. Now I'm not even really worried about that too much. What I'm worried about is what that implies in terms of physics. So this piece here, I could write it like this. As r goes to 0, force of gravity goes to infinity. And you may recall also seeing this notation from math as well. So the arrow means approaches or goes to, gets to that value, right? Well, yeah, mathematically speaking, I can say infinity all I want, but physically speaking, force is never going to approach infinity. Also, physically speaking, r is never going to be 0, right? So if I have these two masses, the closest they can be is touching. So r is still the distance between their centers. So that's not 0. You're never gonna have the two objects that are kind of like completely inside each other. That's very much not physical. So we actually really don't have to worry about that too much. We can just say something like this. As r decreases, force of gravity increases. So that's a lot more physical and a lot more important for us. So this means that as the masses get closer, there is more interaction. This other piece is even more important, and this says as r goes to infinity, force of gravity goes to 0. Now that statement I don't have any kind of problem with. This just means that if the objects are separated by a really large distance, they are not interacting. So that should make sense, right? So for example, our galaxy consists of a lot of stars and a lot of planets and a lot of other things. But our Earth really doesn't feel any forces from all of those distant stars. Even if those distant stars are significantly larger than our own Earth, our own star, the sun. So, yeah. So the distances, galactic distances, or distances between stars, they're so large that all of those other things in our galaxy don't affect us too much. Right? So that's kind of more practical application. So keep this graph in mind, and like I said, especially that last statement, or maybe two statements, where we're saying that inverse square law means that the closer the objects are, the more they interact, and the farther away the objects are, the less they interact. There are other things too that go into determination of interaction. Masses, obviously, very important, right? And by the way, it's called a universal gravitational law. So this works for every mass, any pair of masses, really. So for example, I do this every semester. I think it's worth taking a look at it. So mass of Earth is something like 6 times 10 to the power 24 kilograms. That looks like a large number, right? How big is this number? Well, 6 was 24 zeros, right? Yes, I know you know how to use scientific notation, but it's educational to kind of take a look at that. So this is the mass of our Earth. That's a lot of zeros, right? Now it really looks like a big number. You don't really realize how big these numbers are until you write them out. But the thing is that our Earth is actually really tiny, even in comparison to our Sun. Mass of our Sun is 2 times 10 to the power 30 kilograms, roughly. So I'll change this to a 2 in the front, which actually stops even mattering at that point. And I can add 6 more zeros. Okay, so we could use universal gravitational law. We could use that to calculate interaction between the Earth and the Sun. That's a really big numbers here, right? Well, it can be even more. So, a mass of a galaxy. Actually, I'm not even going to do a galaxy. Anybody knows what is in the center of our Milky Way galaxy? There's a giant black hole. This black hole has a mass of 1 million times larger than the mass of our sun. So I can take that number, right, and add another 6 zeros to it. And I could calculate, use the universal gravitational law, I could calculate how our sun interacts with the black hole in the center of the galaxy. And it actually does, because our solar system travels in a circle around the galactic center. If you're interested in knowing more about that, take my astronomy class. Okay, so our sun does interact with the black hole in the center of our galaxy. Okay, so our entire solar system basically travels in uniform circular motion about the galactic center. Okay, there are about 100 billion stars in our galaxy. So take this number and multiply it by 100 billion. 100 billion is another 11 zeros. So we can add another 11 zeros to this number. Okay? And then there are about 100 billion galaxies in our observable universe. So add another 11 zeros to that. And that's actually a great underestimate of the mass of our universe, because it doesn't take into account things like gas, dust, and dark matter. I'm not going to talk about it in this class. Again, if you want to know more, take my astronomy class. The point is, you can keep going with all these zeros, right? So if you want to know the mass of our observable universe, take that number with all those zeros and probably add another 25 or 27 zeros to it. That's a lot of mass. And yet, even with that, we can use this equation to at least estimate how, let's say, our solar system interacts with the entire universe. It's a really poor estimate because there is a lot of other stuff that's going on, but at least we can estimate this. Or, some people even talk about parallel universes. We can even use this equation to calculate how two parallel universes interact. Again, it's a really poor estimate because of all the other stuff that's happening, but we could at least get an idea. Going the other direction, mass of an electron is 9.11 times 10 to the minus 31 kilograms. So that's that. That's a lot of zeros in the other direction, right? And we can use universal gravitational law to also calculate gravitational attraction between two electrons, or between the Earth and the electron, or anything else in between. So it really is a universal gravitational law. It really works for everything. So as long as you know the masses and you know the distances between those masses, you can use it either to calculate that interaction exactly, or at least to kind of get an idea of what that force looks like. Okay, so all of these numbers that I've given you, except for the mass of the electron, are really approximate. So if there is a couple of zero missing here and there, whatever. I just want you to think about what exactly those numbers represent and how powerful this law is. It's a relatively simple rule, but look at what kinds of objects this can apply to. Okay? So how do we reconcile this force of gravity and this force of gravity? So let's take Earth. This is not drawn to scale. And let's take an object at the surface of the Earth. This is way, 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 way not to scale. So for example, if I drew the tallest mountain on Earth, it would look kind of like this. And I bet you can't even see the little dot that I just put on the surface. That's because radius of Earth is something like 6,000 kilometers, and the highest mountain on Earth is something like 11 kilometers. So anyway, this picture is really not drawn to scale. So we are used to using F with a subscript little g, where we would use the mass of the object times little g. And now I'm telling you that we can use F with a subscript big G, where we're going to use mass of Earth, mass of the object, divided by r squared, multiplied by the universal gravitational constant. Okay? By the way, what is the radius here? Well, remember we said we can basically ignore the size of the object. So basically we're saying that r is the same as the radius of Earth, which by the way you can look up. Okay? So instead of writing little r squared in the denominator, I can write radius of Earth squared. No matter how big that object is, it's still pretty much so tiny that its size is negligible in comparison to the radius of the Earth. So this is the same situation, right? We have two equations to basically describe the same situation. So I can set them equal to each other. I can say that F little g is the same as F big G on the surface of the Earth. I can actually do this for any planet or star or asteroid or whatever, right? So let me set these two expressions equal to each other. And I can cancel MO, and I get an expression for little g. Now remember we said that little g is 9.80 meters per second squared at, on, or near the surface of the Earth, right? Where does that come from? From this expression. So we can take mass of Earth, radius of Earth. It's somewhere in the table in your textbook. You can take a look at that, plug these numbers in, get the value of g. Hopefully you also recall that I told you that something like 20-ish years ago, this value was 9.81 meters per second squared. So that's not because the gravity of Earth has changed. It's because 20 years ago, we didn't have the technology that we have now to measure the mass and the radius of Earth. So once we've remeasured things, we were able to calculate the value of little g a little bit more precise. So this little g is our acceleration of gravity. If I separate these two objects, so here is Earth and here is the object that's not exactly at the surface, I can use this height h above the surface, or also I would call it altitude, to calculate the value of little g at a certain altitude where that object is not on the surface. And then I would write g equals big G, mass of Earth, divided by radius of Earth plus h, the whole quantity squared. I'm not going to box this, but use your good judgment in terms of when and where to use that. And of course, this doesn't even have to be on Earth. You can use any planet. You can use any star. Now, stars don't have a solid surface, so you would say quote-unquote surface of a star. But you can still do this. So if you know the radius of the star and the mass of the star, you can calculate the value of gravitational acceleration near that star, near the quote-unquote surface of that star. Okay? And obviously little g ends up not being constant. It depends on the star or planet or whatever it is you're talking about. and it also depends on the altitude now. The last thing that I'm going to tell you, let's go back, way back to this picture here. So we talked about how to calculate magnitude of this force, but I never told you about direction. So force of gravity is attractive force, right? And I also can label it like this, F2 on 1, F1 on 2. And obviously we can confirm this by Newton's third law. We can write that these two forces are equal and opposite to each other. So if you're talking about two interacting objects, they exert equal and opposite forces on each other. So for example, if you have Earth and you have Moon, even though Moon is significantly smaller, it still exerts the same amount of force on the Earth as the Earth does on the Moon. So the reason that it's the Moon that moves around the Earth and not the other way around is because of the Moon's smaller mass, right? So the forces are equal, but the masses are not. So think about inertia, think about Newton's first and second law. Smaller mass is easier to accelerate. So the Moon is going to orbit the Earth and not the other way around. We'll talk about orbits a little bit more in the next set of lecture notes. But all of this stuff here about universal gravitational law, keep in mind that this really does apply to everything.